Jack Jackson. In this video, we're going to go over a couple of exercises dealing with line integrals. So the first thing to notice is that in the last video, we talked about the idea of a line integral for a line integral over a vector field over some curve, but we did that for 2 dimensions. It turns out that in higher dimensions, we can easily generate these concepts that we introduced previously. And regardless of the number of dimensions, we have a curve in however many dimensions, 2 dimensions, 3, could even be more. And we're integrating over that curve, and the line integral is just the vector field function f dot dr. And the way to get that accomplished, is to parameterize that. So you have to parameterize the curve C in terms of some parameter t, and that gives you your r vector function. Then evaluate your f at that, so you turn f into a function of t. It might be given as a function of, say, x, y, and z instead, but get it as a function of t. And then, of course, you take your r function, take a derivative, which gives you a function here. Both of these are vectors. Do the dot product, that's a scalar function of t. Integrate that scalar function from t1 to t2. So that works no matter how many dimensions you are. So let's do a 3D example now. So the function for our vector field is negative y, comma x, comma 5. So it's a 3D vector field. C is going to be a curve in 3 dimensions as well. It's given by the parametric equations x equals cosine of t, y equals sine of t, and z equals t, where t runs from 0 to 4 pi. And so let's do the integral of that function f over that curve C as a line integral. Actually, I think you should be able to work this one now. So I'm going to let you give this a shot, and then we'll come back and check it here in a minute. So I'm going to ask you to work it. Come back when you're finished. Press pause now. Okay. So here's what we have. Those parametric equations boil down to this vector function for the position. R of t is cosine of t, comma sine of t, comma t. T goes from 0 to 4 pi. And you should probably be able to kind of visualize this first of all. Notice that if you just ignore the z, you've got x equals cosine t, y equals sine t. Well, that just graphs the unit circle. So as far as the x and y's, this is just the unit circle going around the unit circle actually twice. Okay, but the z values are the value of t, so that's going up. So you're actually not just tracing around a circle. That circle is being stretched out into a circular helix, like a spring or a spiral going around. So if we looked at this spiral directly from the top, it would look like a unit circle, and if we look at it, more from the side, it looks like a spring. Okay, it's called the helix. Okay, now we're going to need dr, so we just need the derivative of this guy, which means you just take the derivative of each term separately. Derivative of cosine t is minus sine of t, derivative of sine of t is cosine t, and derivative of t is 1. And dr has the dt as part of it as well. So that's r prime of t, dt is what's meant by dr. Then we do f, it's minus y x 5 is what it was given, but now we want to parameterize that using this. So where the y is replaced by sine of t, and where the x is, that's replaced by cosine of t. And so there we have f as a function of t. So we just take this f vector function, dot product with this r prime, and then integrate with respect to t, where t goes from 0 to 4 pi. So now we've got it almost into a calculus 1 integral. Once we do this dot product, we'll have it. So minus sine of t times minus sine of t is sine squared t, plus cosine of t times cosine of t is cosine squared t, plus 5 times 1 is 5. Sine squared t plus cosine squared t is 1. 1 plus 5 is 6, which I can bring out front. And that reduces down to an extremely nice integral for us to work out. 6 times the integral from 0 to 4 pi of dt. And the antiderivative of dt is just t. And so we have 6 times t evaluated from 0 to 4 pi. So that's 4 pi minus 0 is 4 pi times the 6 is 24 pi. And so the integral is 24 pi, or approximately 74.4. And you can see here the see it graphed. I have this where we could kind of look at it a little bit. I think somewhere. Let's see. Here it is. Here we have, you can see the unit circle there when we look straight from above. And the vector field also is, you can definitely see a circular motion to that vector field. So this is rising up as we go. And so you're going to see it going, we're tracing T route, we're going around this circle in this direction, the same direction as the rotation, which indicates that we're going to get a positive integral there, and it's also rising up, and the z component of these vectors is all positive as well. So looking, some different versions there, you can look at it from the side, and you see a, sine or cosine wave basically going on there, and you can kind of see what some of these different vectors look like. It's kind of cut off. The vector field doesn't graph up as high as the curve is going here. So in this particular one, we got some dead space down here and some missing things up here for vectors. But hopefully you can get kind of the idea of some patterns in those vectors and in the helix as we sort of move it around from different viewpoints. You can kind of see what's going on there. Okay. All right. So anyway, that's one exercise there. Let's try a different one. This is more of a concept question. So below are several 4 different directed curves placed in certain vector fields. So determine if the line integral of the vector field over that curve is either positive, 0, or negative. And you should be able to do this without performing any kind of calculations if you understand basically the basic concept of what's happening with the line integral. So once again, I'm going to ask you to work this yourself. When you think you've got an answer for all 4 of these, then come back and we'll check them. Press pause now. Well, it turns out that this first one, the integral is actually 0. This is a circle centered at the origin, or semicircle centered at the origin, and all these vectors point away from the origin. So that means that every one of these vectors is perpendicular to the curve. Vectors perpendicular to the curve don't either add or subtract anything from the integral. So all those dot products would be 0, and in fact this turns out to be a 0 integral for the line integral. For the next one, the line integral is positive. Every one of these vectors has a component that's going in the direction of the arrows of this curve, which is just a straight line, a directed line there. And like, for example, vectors in here are going to have a downward component, but they have a component that's also going in the direction here. And every one of these has some component going there. So every single vector along here is going to contribute positively to that line integral. So that's going to be a positive one. Now this one here is a little harder to see because what's happening is different in different quadrants. Now in the bottom quadrant, quadrant 4 here, these vectors are kind of pointing down and to the left, as is the curve. So this part here, if you just integrated, say, from the x-axis, that point down to here, we would get positive because the vectors are pointing, at least a component of the vector is pointing in the direction of the curve. However, if you look at the first quadrant, these all have components that are going opposite the direction here. And the size of the components that are going against the curve here, and the length is longer as well on the curve, but the size of the components going against the curve is going to be bigger than the part down here that's going against. So we're going to actually end up with more negative than positive here. So ultimately this is going to be a negative integral. The last one is positive. no matter which quadrant you're in, if you look at the vectors, they will have a vector component that is going in the direction. So all of these vectors are going to at least add something to the derivative here, something to the integral here, and then same way in the first quadrant as well. So all of those vectors have at least some part of their vector, some component going in the direction of the curve. In other words, in the direction of the tangent line of the curve, unit tangent vector. So we should be able to understand something about that, just based on the mainly the direction of these vectors and possibly their relative sizes. Okay, so once again, the intuitive idea here is that the line integral is basically adding up the contribution of the vector field, the part that's going in the direction of the curve. That's going to contribute to the integral. If it's going in the same direction, that's going to contribute positively to the integral. If it's going the opposite direction, it's going to contribute negatively. And if it's going perpendicular to the curve, that doesn't add or subtract anything from the integral for that portion.